Hi, so today I'm going to talk about support for data warehouse in RDBMS. So this is the beginning, this is a new module in which we are basically talking about what kind of support RDBMS have for data warehouses, and also we'll be talking about SQL, the new features that have been added in SQL. So that will be the second lecture in this module. And this module is important mainly because most of the data warehouse implementations are on top of relational databases, right? So it is important that the current relational engines support data warehousing in a big way, right? So that the data warehousing projects are successful and people are able to easily deploy their data warehouses on top of relational databases. So let me begin. Again, what I'm going to cover is not an exhaustive list of features that have been added in RDBMS, but it is just a representational. It is just kind of a representative list of topics that I've chosen, mainly, and the criteria for choosing them is mainly based on what we have covered in the course so far. And most of the material for this presentation has been taken or adapted from Oracle 9.9 11G data warehousing guides available on the Oracle site. And as a result, the contents have a bias towards data warehouse features supported by Oracle. Many other RDBMSs also support similar features, but you'll have to check exact implementation and of these features and how they are supported. So there might be slight differences. So let me begin this talk. So there is support for aggregates, and most RDBMSs have aggregate navigator middleware. Then there is support for partitioning, and I'll also be talking about even if there is no support for partitioning, how you can actually build partitions in a relational database. Then we talk about materialized views, and also on bitmap index and bitmap join index. So there is support for both. And then there is a concept of dimensions where you can actually specify the hierarchical 1 to n relationship between the different levels of the hierarchy. And then there is also talk about online aggregation, so which is again linked to the concept of aggregation, but this is a nice feature that is supported in many RDBMSs, and it it actually starts giving you early results of aggregation, which might take a long time to execute, right? And we'll also be talking, as I said, about SQL extensions, which will be covered in the next lecture. So aggregate and aggregate navigator. So most RDBMSs have support for aggregates and aggregate navigator in the form of aggregate navigator. And we have discussed this already in a lot of detail when we talked about aggregation. So I'm not going to repeat all that. So let me tell you, so this aggregate navigator helps the RDBMSs to improve performance of queries requiring aggregates and to match performance of multi-dimensional databases. So if you remember multi-dimensional databases, which are covered in module number 6, they are highly suitable for building aggregates, right? So relational databases have to do something to catch up with the performance of multidimensional databases in terms of especially when it comes to aggregates. So this concept of aggregate navigator is very useful. So we have aggregate navigation algorithm and metadata. So these two things, so aggregate navigator uses the aggregate navigation algorithm and the metadata to target the most suitable aggregate for a given query. So it does the matching. And while discussing aggregates, I also mentioned about an article by Kimball in which he refers to aggregate navigation with almost no metadata, right? So So those things also you can look at, but in general, Aggregate Navigator helps in improving the performance remarkably. And another important thing is that users and queries need not be aware of existing aggregates, so that we have already discussed and implemented using metallized views. So the concept of metallized views is more general, right? It's than the concept of aggregation. So it is implemented using metallized views. So metallized views we are going to discuss in the coming slides. Then we have talks about partitioning. Then we need to talk about partitioning. So partitioning is also very well supported in most of the RDBMSs. So data warehouses often contain very large tables and require techniques for both for managing these large tables and for providing good performance across them. So for this purpose, we have this concept of partitioning. And so partitioning is basically that you have a large table and you partition it with respect to some criteria into smaller partitions. And so the original table which you partitioned does not exist anymore in physical form, but it is still there in the logical form, right, or in a virtual form, right? So you can actually query the original table as well, and you can also query the partitions, right? So now I'm going to tell you a little bit about, even if it is not supported, like partitioning is not supported, one can create them using the concept of views. And what we do in this is that we manually move the data from the table to be partitioned to its partitions, which are again tables, right? And create a view using union of partitions, giving an illusion that the original table still exists. So from a user's perspective, the original table exists and all the partitions also exist, although we don't call them partitions, but they act as partitions, right? So this way you can have a feature of partitioning in any RDBMS. And then now let me come to types of partitioning. So here Oracle offers 4 partitioning methods. So range, and this was already discussed when we discussed partitioning, so I'm not going to do it again. Then we have hash partitioning, then we have list partitioning, and followed by composite partitioning. So let me give you some idea about these different kinds of partitioning. Hash. So hash, as you know, hashing is a very standard technique in computer science. So hashing does what is it is known for evenly dividing data or distributing data among the partitions or devices, and it is a easy to use partitioning. Only thing that you need to specify is, specifically in Oracle, is just the number of partitions, which happen to be in the powers of 2, right? So Oracle uses a linear hashing algorithm. So linear hashing is a dynamic hashing technique to avoid skew in the partitions, right? And number of partitions should be in powers of 2. So it could be 2, 4, 8, or 16, or any other power of 2. And the limitation here is that users cannot specify alternate hashing functions or algorithms. So whatever is there by default, only those would be used, right? So let me give you some example. So create table sales hash. That means sales table has been partitioned using hash partitioning. So sales, so this is the schema: sales ID, salesman ID, salesman name, sale amount, and week number, and partition by hash on the salesman ID, right? And I'm saying that I need 4 partitions, so which is a power of 2. So 4 partitions would be created, and these partitions are stored in data 1, data 2, data 3, data 4, which happen to be table spaces. So table spaces are like virtual tables, or kind of a virtual area which can have multiple tables, right? Now comes list partitioning. So list partitioning enables you to explicitly control how rows map to partitions. So basically in hash and range partitions, so you don't have a control. So you just give a criteria, and based on this you can the partitioning algorithm would distribute the rows to partitions. But here in this case of list partitioning, you can actually have a control of which rows goes where, right? So specify a list of discrete values for the partitioning column in the description for each partition. And it is different from range partition, where a value is associated with the partition where a range of values is associated with the partition, and with hash partitioning where you have no control of the row to partition mapping. And advantage is that you can group and organize unordered and unrelated sets of data in a natural way, right? Say, let us see an example. So create table sales list. So salesman ID, the same schema, right? And I'm partitioning by sales state. Okay, so I'm saying partition sales west, values in California and Hawaii, east New York, Virginia and Florida, partition sales central in Texas and Illinois, right? And this creates a partition. So you can see that these state names do not follow any range or kind of any pattern. So you can specify a list, and you can give them appropriate names to represent, say, different regions in a country or in the world, right? So this is an example of list partitioning. And then we have composite partitioning. So composite partitioning combines range and hash partitioning. So it allows you to do that. So first distribute data into partitions according to the ranges, and then use hash partitioning to further divide the subpartitions within each range partition. Now the next topic is metallized views. So this also we have discussed in detail, and they are also supported in most RDBMSs. And these are the four kinds of metallized views supported, and these are supported again in Oracle. So with aggregates, with joins, with both joins and aggregates, and nested metallized views. So these are the four types that are supported in Oracle, and this is supported in Oracle 11G. So this is how it looks like. So I'll just write the whole thing, and then I'll discuss this. Yeah. So you can see that so in Oracle you have to create a metallized view log, right? So that fast refresh, there is a technique for refreshing the metallized view in an efficient way, so that is called as fast refresh. So logs need to be created so that you can do a fast refresh. So now if you look at the definition, so here I've created the log, and then I have created a metallized view sum sales, which is containing only aggregates. Parallel, so if there is a parallel architecture, I can do that. Build immediate means this metallized view will be built as soon as this query is executed, right? Okay. And so there is also an option of build deferred, so you can defer the building of this aggregate, right? Refresh fast, I just explained this, so this is linked to the concept of this log. And then this is the definition of the view, right? This is the aggregation which we have defined, and that's how it is created. So exact syntax is not important, and it will vary from one RDBMS to another. What is important is that you have to see that what kind of support these systems, these RDBMSs are providing for metallized views, and maintenance is one of them, one of the important issues. So most of the RDBMSs take care of provide mechanisms for maintaining the views in any way you like, the view maintenance policies that we discussed earlier. So most of them are implemented in some form. Sorry. So this example creates a metallized view that contains aggregates on a single table, right? And because the metallized view log has been created with all reference columns in the metallized views defining query, the metallized view is fast refreshable, so that's what I mentioned. And if DML is applied against the sales table, then the changes are reflected when the commit is issued. So as soon as there is any query on the base table from which it has been created, the view will be maintained immediately. So this comes under the immediate view modification strategy for maintenance. Then we have nested metallized views. So this is another new concept that has been introduced recently. So a nested metallized view is a metallized view whose definition is based on another metallized view. And also a metallized view can reference another relation in the database in addition to referencing metallized views. So what it does is that the metallized view definition, say MV2, is based on some expression involving MV1, which is another metallized view, say joined with a table that is there in this. So it could be something like this, right? So that's why we say that it is nesting of metallized views, and basically it means that a metallized view has been defined using another metallized view, right? So what is the advantage of doing this? So in a data warehouse, you typically create many aggregate views on a single join, right? For example, roll up again different dimensions. So you want to do a roll up again on different dimensions that are present in the star schema. So what happens is that so incrementally maintaining these distinct metallized aggregate views can take a long time because the underlying join has to be performed many times, right? So what we do is we create this nested view or nested metallized view where this problem is taken care of. So using nested metallized view, you can create multiple single table metallized views based on a joins only metallized view, and the join is performed just once. So this is the basic idea of metallized views, nested metallized views, and it helps in reducing your computations. And nesting is possible only with metallized views, so there is a restriction containing only joins or aggregates, right? So you cannot do both. You cannot nest a view which has both join and aggregate, so that's a restriction. And metallized views with joins and aggregates are implemented using nested metallized views. So basically what you do is, say MV2, I can say this is suppose trying to do a join, right, and metallized view 1 which is an aggregate. So I can do something like this. So this is how join and aggregation are both supported. Similarly, I can do something like summation on MV1 join T, and this can go into MV2, right? So here it is a join and aggregate in a different order. So this is what is the concept of nested metallized views. Again, here I'm not trying to give you the exact syntax, because that syntax will work only for Oracle. So it is highly recommended that you look at the syntax for the RDBMS that you are using for your data warehousing projects, and see if nested metallized views are supported or not, and accordingly look at the syntax. Then let us come to bitmap indexes. Again, this has already been covered, right? So there's nothing much to add here. So only thing is that I'm just adding some more perspectives to this. So bitmap indexes are widely used in data warehousing environments, which typically have large amounts of data and ad hoc queries. And for such applications, bitmap indexes provide reduced response time for large class of ad hoc queries, reduced storage requirements, because as compared to other conventional tree or hash based indexing structures, this we have already seen, and dramatic performance gains even on hardware with a relatively small number of CPUs and small amount of memory. So it is like not very compute intensive. And fully indexing a table with a traditional B-tree index can be prohibitively expensive in terms of space, because the index can be several times larger than the data in the table. So B-tree indexes take up a lot of space. So bitmaps offer a cheap alternative in terms of space, and at the same time provide you with performance benefits, and are typically use only a fraction of the size of the indexed data in the table. And this topic we did not discuss in detail, so I'll give you some details of this, right? So in addition to a bitmap index on a single table, you can create a bitmap join index, so BJI, which is a bitmap index for the join of 2 or more tables. So it is just like pre-computing the join and keeping it, and instead of keeping the tuples, you store the bitmaps of those tables. So it's a space efficient way of reducing the volume of data that must be joined by performing restrictions in advance, right? And for each value in the column of a table, a bitmap join index stores the row IDs of corresponding rows in one or more tables, and they provide a faster way. So we know the pattern in data warehousing. So we typically perform a inner join, equi inner join between the primary key column or columns of a dimension table and the foreign key columns in the fact table. So this is what is the typical join, and they are much more efficient than metallized join views for metallizing joins in advance. So this we have already seen. Okay, so what happens is, because this is happening because metallized views do not compress the row IDs of fact tables, so they work with the row IDs as such, but in bitmap indexes we compress them, so that leads to less storage and make them more efficient than the corresponding metallized view for performing joins. Now we have a concept of dimension, which is also supported in Oracle. So we know that a dimension is a structure that categorizes data in order to enable users to answer business questions, and these are some commonly used dimensions. So in Oracle database, the dimension information itself is stored in a dimension table. So there is a concept of dimension table so which contains hierarchical information. So I'll straight away talk about a particular example right, so that you can see. Okay, so sorry, I missed the slide. So dimensions do not have to be defined explicitly, right? However, if your application uses dimensional modeling, it is worth spending time creating them, as it can yield significant benefits, because they help query rewrite perform more complex types of rewrites. So that is the idea. And in spite of the benefits of dimensions, you must not create dimensions in any schema that does not fully satisfy the dimensional relationship. So dimensional relationship is basically about hierarchies. So let us see how it is supported. So before you can create a dimension object, so dimension is a database object in Oracle, and the dimension table must exist for which you want to create this object, right? So and it should contain the dimension data. So you can create a dimension using create dimension statement. So let me give you an example. So you can declare a dimension, product dimension, which is based on the product table that you have, right, which contains levels, product, subcategory and category. So what I can do is create dimension, product dimension, level product is, and you have to map it to, so you have to define a level, which I am saying is product, is a level, and you have to map it with the attribute in the product table. right? Then I define another level which is subcategory, and you have to map it to the subcategory column in the products table. Then we have another level which is the category, and again it has to be mapped to the category, uh, product category attribute in the products table. So this is the first step. Now once you have defined these levels, so now you have to define the position of these levels in the hierarchy, right? And for that you have to create a hierarchy, and you can appropriately give it a name. So in this case, this hierarchy can be called as the product roll-up hierarchy or something, some name you can give to it. So let us see how it looks like. So create dimensions, dimension, product dimension. So this is the same thing, and then the next step is to specify the hierarchy. So what we have done is, so you can see hierarchy I am defining, and I am giving it a name, product roll-up. Product is a child of subcategory, and subcategory is a child of category. So you have defined a hierarchy or one-to-many relationship between subcategory and category. So one subcategory, so this kind of relationship, one-to-many relationship. So one subcategory, one category would have multiple subcategories, and one subcategory would have multiple products in it. So this way you can define the hierarchy, and this can be used when you are doing a roll-up, right? So the concept of dimension is supported in Oracle, and you can see how you can create a dimension, and so you have to, so if you have a dimension table like product, right, so you have to create a dimension on top of that, and then you have to specify the hierarchy. And now the last topic for in this section is online aggregation. So here what we do is we have this concept of online aggregation. So consider, so let me explain this by using an example. So consider an aggregate query. Example, finding the average sales by state. So this is so calculate the average sales by state over a period of say 5 years. So the question is, can we provide user with some information before the exact average is computed for all states? So can show the current running average for each state as the computation proceeds, or better, if we use statistical techniques and sample tuples to aggregate instead of simply scanning the aggregated table, we can provide bounds such as the average for a particular state is 2000 plus minus 102 with 95% probability or confidence. So this is basically interval estimation, right? So these are the options that we are talking about. But what we do in online aggregation is that we try to give you the progress as the value, as the current value of average approaches the actual value. So we are giving you the value at different stages, and when the aggregation completes, so you get the actual value. So this is what we do, and for performing online aggregation we use what are called as non-blocking algorithms. So an algorithm is said to be blocking if it does not produce output tuples until it has consumed all its input tuples. So typically joins are non-blocking, again depending upon what kind of algorithms you are using for performing the joins. But typically what I need to do is that I have two tables and I want to do a join based on the common column. So I take the first tuple here and match it with the first tuple in the other relation, and if the join condition is satisfied, I output it, right? So join algorithms are typically non-blocking, right? So but any kind of sorting is blocking. So so which join algorithm for aggregation? So you can use the simple join, so we call it the nested loop join and hash join, versus sort merge join. So sort merge join is not preferred because it is non-blocking, whereas nested loop join and nested block loop join can be used for performing the joins, right, for online aggregation. And hash based aggregation versus sort based aggregation. So hash based would be preferred because of the non-blocking nature. So this online algorithm basically say suppose I have this query. So select l.state, that is location.state, and average sales, that is coming from s.sales, and I'm performing a join, and I'm doing a group by L state. So it will look like this, that state 1, what is the value, right, state 2, what is the value, this is what it is going to give me, average value, sorry, okay, and then state n value. So in online aggregation what you have is, we typically have a progress bar, right, and it tells me that how much progress I have made so far for this state, for this state, and for this state, and the corresponding value keeps on changing. Say it'll change, it'll keep on changing with the progress. So it is just like when you are downloading a file, so you get the progress bar, right? So it tells you this. And in addition, most tools that allow you to do online aggregation also give you a radio button, which is using which you can prioritize different states. So if you are very interested in state 2, so I can say that I'll prioritize this, so this would get priority. So more resources would be allocated in calculating the average sales of state number 2, right? So I can give you a very interesting analogy for this with respect to election results. So as and when the counting starts, the trends keep coming out, right? And if there is a very high profile contest at a particular seat, so I can prioritize that. So that means I can put more resources or more people on counting the votes polled in that particular constituency, right? So I can prioritize that. So this is what is online aggregation, and it is also typically supported by most RDBMSs, right? And sometimes they are part of the OLAP tool that you are using on top of relational databases. So with this, I wind up this section. So here I basically looked at 5 or 6 concepts or features that are supported. So there's a whole lot of list of features that are supported by relational databases, right? But as I told you, I focused mainly on those features which we have discussed in the course so far, right? So there are techniques for compression, right? There are techniques for making the ETL faster, right? There are techniques for making the maintenance of metallized views faster. So there are a whole lot of features that have been added, and continually they are being added, right, even now. So implementation of data warehouses on top of relational databases makes sense, right? Because relational databases are kind of, relational database vendors are incorporating new features to support data warehousing. So in the next lecture, I'm going to talk about some features that have been added in the SQL, right? So I'm now going to focus attention on SQL, right? So that would be the next lecture. Thank you.